Thank you, Ethan. And first of all, I'd like to say that it's an honor to be here at IMPA. And so, as the title says, this talk is about Hertzsprung generalizing problem in Unix conjecture, which are essentially problems involving local cohomology and its finiteness properties. And it's a joint work with Professor Cleto, Miranda, Neto, and Professor Rafael Holanda. So before start, let me make some conventions. So here, our rings are assumed to be Noetherian and commutative with unity. And by finite model, I mean finitely generated models. So let's start by recalling the definition of a local cohomology of a model M with respect to an ideal I, which is defined just as this direct limit of X models. Despite its idiosyncrasy of this theory, the local cohomology has the remarkable property of not being finitely generated in general. In order to illustrate this phenomenon, we have, for example, this result from Hellos, which states that if the base ring is a regular local ring containing a field, then the local cohomology is finite just in case that it vanishes. And so it is quite natural to consider the so-called finiteness problems of local cohomology, which includes the finiteness of the set of associated primes, minimal primes, bad and best numbers. And this work is indeed addressed to study the finiteness of the set of associated primes of both ordinary and generalized local cohomology. But first of all, I'd like to say some words about the technique that is often used in order to approach such problems. It's about Grothendieck's conjecture and Hertzsprung's problem. So Grothendieck's conjecture was established in 1968, and it asserts that this construction, I mean this home model, should be finite for every finite model M. And this is indeed the case, at least the ideal is maximal, because at this situation the local cohomology is Artinian. But it's false in general, and the first counterexample was provided by Hertzsprung in 1970. And besides this counterexample, he also introduced it in order to generalize the whole situation, the concept of icofinite models. So we say that a model M is icofinite if its support vary and this extra modulus is finite for every index. And then Hertzsprung posed the following natural question, which is try to understand when the local cohomology is icofinite for every index. And I mean, it's not true in general. I mean, the Hertzsprung's counterexample about Grothendieck's conjecture already shows that it's not the case. But Hertzsprung could find some positive answers, at least when the base ring is a completely regular local ring, and the ideal satisfies the conditions. I mean, if the ideal is principal ideal or one-dimensional prime ideal. But what's the connection between this problem and the problem about the finiteness of the set of associated primes? So first of all, it's worth to talk about Unix conjecture. It was stated in 1990, and it asserts that, at least in the local case, we should expect the finiteness of the set of associated primes. But it's not true into its full generality. And the negative case, I mean, even in the non-local case, we have a counterexample done by Sinch in 2000, and in the local case, we have a counterexample done by Katzmann in 2002. But still, the Unix conjecture has some positive answers, typically in lower dimensions. Why is that? So the idea is that we have a connection between Unix conjecture and Hertzsprung's problems that explain why Unix conjectures has positive answers in lower dimensions. And the idea here is that all icofinite models have a finite set of associated primes. What justifies this is just the fact that if M is icofinite, then this home model is finite, which implies the finiteness of the set of its associated primes. But it turns out that this set is equal to the set of associated primes of the model, which justifies the finiteness of the set. And so we can read this result as a kind of approach in order to study the Unix conjecture. We just need to prove the local cohomology is icofinite. And this is indeed the case in lower dimension, at least if the dimension of the ring is no more than 2, as was proved by Faridian. So at this case, we have the icofiniteness of the local cohomology. But in higher dimension, this is not the case in general. I mean, there are some counterexamples that shows that the local cohomology can be not cofinite. And it's necessary to introduce a weaker version of the icofiniteness. And in order to explain that, I need to introduce the concept of Rickless-Scaden models. So a model M is called Rickless-Scaden if its quotients have a finite set of associated primes. These models contains, for example, all Noetherian and Artinian models. And with this notion, we can introduce the concept of I-weak cofinite modulus, which are modulus supported over I, and such that actual modulus are weak on a scalar. And it turns out that this notion carries the same finiteness property with respect to the set of associated primes. And this is indeed the suitable notion we must require in order to handle the three-dimensional case, at least in the local setting, as it was showed by Quoos, Gold, and Huang in 2015. So at this case, the I-weak cofiniteness is what you need to have in order to provide the finiteness of the set of associated primes. Okay, so now let's talk about our work, our results. So as I talked a few minutes ago, our goal is to try to understand finiteness properties of this object, which is the generalized local cohomology, which has something to do with a pair of modulus, as you can see. This notion generalizes the ordinary case, by just taking M equals to the base ring. And we can ask ourselves, why should we care about this object, since we already have a well-established theory in the ordinary setting? The point is that you can use this object to provide, for example, some freeness criterion for modulus, and also a more general theory involving modulus of deficiency and canonical modulus, and also in order to provide some results by using prescriber upper bound of projected dimension of modulus. But here we are interested in its finiteness properties. So we basically are considering the Hertzsprung's problem and the Hinrichs conjecture with respect to this object. And our first contribution has something to do with this result from Maffei, which assesses the finiteness of the set of associated primes of H1, when the module M is finite and the second module N is weakly scalar. And it turns out that, in general, we like to leave fixed the first hypothesis, M to be finite, because it ensures some nice functorial properties of the construction. But with respect to the second module N, we can make the following natural equation, which is try to understand what happens with the finiteness of H1 when N is no longer a weakly scalar. And then we provided two examples, both of them constructed over a polynomial ring with coefficients in an infinite field. And in the first one, it happens exactly what you expected for. For some non-weakly scalar module N, we can describe explicitly an infinite family of associated primes for the model H1. But in the second example, we already get a non-weakly scalar model N, but at this case, we get the finiteness of the set of associated primes of H1. And it's a little bit more dramatic in the sense that here, the model M can be any finite model. Obviously, we take care to ensure that it's not a trivial construction in the sense that this model is non-zero, at least in the case that the first model is free, or it's equals to this model here. So it was our first contribution, which shows a kind of chaotic pattern of the associated primes of H1 when the second model is not weakly scalar. Our first contribution had something to do with this result that can be read in some sense as a kind of principle of the whole theory of I-cofiniteness for ordinary local cohomology. And it asserts that if the ordinary local cohomology is I-cofinite for every index I different to S, then HS will be also I-cofinite. And we can understand the importance of this result if you look, for example, for the fact that the I-cofiniteness of the ordinary local cohomology can be proved in the case where the ideal is generated by an M sequence, and also in the case where the ideal has a cohomological dimension equals to 1, by using exactly this result. And our goal here was to try to understand if it's possible to generalize this concept with, this result with our I in the generalized local cohomology. And in order to do that, it was necessary to make some technical definitions. It was necessary to introduce the notion of a pair of I-cohomological injective modulus, which requires this zero local cohomology to be injective for every AI appearing in some injective resolution of N. So with this technical definition, we can indeed provide the version of the result from Marley and Vasilev for this case, for the generalized ordinary setting. And we shall see the applications of this result in the next slides, but obviously I'd like to make I'd like to say some words about these technical definitions here. And the first point I'd like to clarify is the fact that we can use the minimum injective resolution as a kind of a test resolution, in the sense that if this object here is not injective for a minimal injective resolution, so it will happen again for every other injective resolution you may choose. So this is the meaning of to say that the minimum injective resolution can be used as a test resolution. The second point is that we can use this definition in order to provide a calculate of freeness criteria, in the point that if the local ring R is Gorenstein, then to ask the module M, the pair MR to be I-cohomologically injective is the same to ask the module M to be free. And also this situation remains true if you replace the ring R by any Gorenstein module M. Okay, so now let's talk about some numerical invariants that we use it in order to understand and to prove the I-weak finiteness properties, and as a consequence the finiteness of the set of associate primes of our local cohomology models. The first numerical invariant that we introduced was the generalized version of the cohomological dimension. Now it's about a pair of modules, and it's defined as the last index I such that the local cohomology does not vanish. And so by assuming that we are dealing with a pair of I-cohomologically injective modules, we provide the I-weak finiteness when the cohomological dimension is equal to 1 or 2. And at this second case, we indeed proved that the I-weak finiteness is an equivalent property between H1, H2, and not just these two modules, but with respect to these four modules, in the sense that if this property holds for one of them, it will still hold for all of them. With respect to the cohomological dimension, we also provide a count of to show that this upper bound is sharp in some sense. So first of all, I'd like to say that in this paper we had this kind of upper bound. The cohomological dimension is no more than the sum of the projective dimension of M together with the cohomological dimension of the ideal I with respect to N. But we could show a situation where this bound is sharp. So again, by assuming that we are dealing with a pair of I-cohomologically injective modules, if you choose an integer n equal or bigger than this cohomological dimension, then by looking for this set A, if for some integer k, it's such that the generalized local cohomology is I-weak finite for every index I living in the set A different from k, and also hk is not I-weak finite, then not just n will be equal to this cohomological dimension, but we can prove that this bound here is indeed sharp. Okay, the second numerical invariant we have studied was the so-called Gorenstein projective dimension of M with respect to N. We define it as the last index I such that this X module does not vanish. And by using this number, we constructed, not we, but not us, this numerical invariant was introduced by Divanesa and Karimi. It doesn't have a special name, I just call it by Ho, and it's defined as the sum of the Gorenstein projective dimension together with the dimension of the tensor product. And the both authors studied the I-cofiniteness when Ho is not bigger than 2. And what we studied was try to understand what happens for higher values of Ho. And again, in the context of being with a pair of I-cohomologically injective modules, we proved that this is the case. The I-weak finiteness is ensured for every index if Ho is no more than 3. And when Ho is equals to 4, we proved that the I-weak finiteness is an equivalent property of H1 and H2. We also proved the finiteness of the set of associate primes for every index I different to 2. And we just kept studying the case and proved that with this additional condition here, if the dimension of the Ho module is not bigger than 3, then we can prove the I-weak finiteness for every index. This is indeed the case if the module M has a finite projective dimension and it's not a free module. But if you don't have this hypothesis, if you don't know about the finiteness of the projective dimension, you can replace this hypothesis with this another one, which is much more technical, I know, but the point here is that if you look for this result with respect to the ordinary case, which means that you should take M to be equals to the base ring, this number here turns to be exactly the dimension of the module N. And then this result turns to be a criterion for the weak finiteness of local homology for four-dimensional finite modules. And here I'd just like to say that the weak finiteness, which means, let me just put here. So to say that this module is weak finite means that these action modules must be weakly cascaded module for every I in J. And the point here is that we can replace all of these requirements by just asking this module here, module home, to be weakly cascaded, which corresponds to the case where I is equals to 0 and J is equals to 2, which is a very simple situation. Okay, so this is what I'd like to say. Thank you for the attention.